Okay. Morning. Good morning, Brandon. Good morning. I got you. Okay. Yeah. Good
Morning.
morning. Good morning. Um, yes, Tuesdays. If that doesn't work, we'll Zoom or call. Okay. Good morning, Alexis. Oh, the real person. All right. All right. Excellent. Good morning, Xavier, also a real person. Always has been. We got like so much three-dimensionality today, and Brittany, more three-dimensionality, and Xavier, or I just said Xavier, but yes, six-dimensionality. Judith, Charlene, good morning, good morning. Anissa, Maria, good morning, good morning. Chat. Uh, good. Sorry. Good morning, Gaia. Good for the double. Good morning, Judith, for the double. Good morning, Chanel, for the good morning, Chanel. Good morning, Maria. Good morning, Ryan. Good morning, Direct Chat. Good morning, Mickey. Good morning, Brittany. Good morning, Adenelsi. Good morning, Charlene. Good morning, Ethan. And good morning, double, triple Alexis. All right. Let's actually, all right. All right. I'm just going to roll. If that's okay. Did I say? And Juan, I'm sorry. Good morning. Yeah, I think I'm just going to get straight to it. If I can, if I may. I want to pick again. This is all in the. So I'm just talking. I mean, physics here. All in the context of the of that homework called work done by non-constant forces. All in the context of that, and helpful to that. But I'm not. But I'm just talking about the concepts of it. So it's like lecture. So here is okay. A couple of highlights of where we left off Monday. Um, First of all. Second of all, um, okay, quick review. Sorry. No, you should not. Sorry. A direct chat. No, you should be angry at me, or no, if you did not receive your grade yet, you should not be worried. You should not take it personally. You should not think it means anything. You should be frustrated with me. I mean, I hope you're not, but like you will get it soon. Um, No, okay, you're very kind. No, but honestly, no. But I am like, it's coming. They're just you should just be like, oh my God, he's so slow. I can't believe he only gets like done a day. But they're just still coming, and you should not take it as a reflection on you in any way. And I'm just responding to a direct chat, people, about the typical topic of like that I'm still dribbling your midterm exams back to you. Many of you, like some of you have gotten them. An increasingly number of you have gotten them, but some of you definitely have still not. And again, I just want to repeat, if you did get one and you have questions or issues, text me or email me and we'll set up like a phone call or Zoom or whatever, or you'll come to office hours, but I know those are very limited in time is whatever. But on the other hand, again, for those of you who haven't gotten it back, if it's starting to freak you out, just text me or call me and like we'll either talk about it or I'll like sit right there and do it or whatever. But okay, but so no, you should not. Sorry. Well, on that, sorry, another thing in the direct chat. Okay, slightly more complicated, but as far as the final exam, I'm going to be talking about it directly all next week, the last 2 weeks of classes. Like they will be focused more explicitly on the final exam, the logistics of the final. So yeah, I'm just trying to sort of finish the material right now. So this is another question in the direct chat I'm just responding to. Um, I can tell you a couple things quick. The format of the exam is the same format as last time. Like you're going to take it home. You're not going to sit in a room for it during exam periods or anything like that. Like when we have our last class next Wednesday, tell me if I'm wrong about that, by the way, but I believe our last class, is a week from today. And when we have that last class, that's like it for us seeing each other until I see you next semester, I hope. So then essentially the final exam will be posted. This is not exact what I'm about to say right now, but this is the basic idea is that I will post it that Thursday night, like a week from tomorrow, or possibly Friday night, like a week from two night from now. And then you'll have until Tuesday of final week to turn it in. Like basically you have the long weekend, you have the weekend and Monday. So essentially that's the idea. It gets posted Thursday or Friday, and then it'll be due probably Tuesday of final week to send it back. And the exact content I'm going to be more clear about um, in the last two classes of next week. Wait, does that hold on? Oh, so yes. Okay, thank you. Okay. That's a basic idea. I should tell you one other thing though, but wait, first of all, honestly, the person who just asked me, I mean, obviously that's a very fair question. That's a very important question. I'm just I I'm a little bit more prepared to be more clear about that on Monday, but did that sort of answer what you just asked? Well, okay. I sort of hope it okay. Okay, okay, okay. Yeah, homework. Yeah, the more, all right, you know what I want to say right now? No, fair enough. Um, okay, I'm gonna say right now, the very last homework that's it, we're right now dealing with, what I'm dealing with today in class is was is it called homework 10. Um, and we're still in the second to last week of classes, so I don't think that's that crazy. I mean, it's all a little bit crazy right now, but I totally agree. Okay, to whatever extent this is, even though this is sort of always true anyway, right now I'm taking what you're saying seriously. I'm going to put in, I'm putting in Google Classroom right now that homework 11 that is supposedly due on Monday, I'm adding a note to it right now that says very optional. Okay? Because you're right. So you totally don't have to do homework 11. All right, I'm going to talk about the content of it sort of quickly next week, like in one half of one period. I'm not going to make a big deal about it. Well, I'm not going to make a big academic deal about it. So I'm going to say the homework is very, very optional now. At some level, all of these homeworks are optional at this point. I mean, like you don't get punished for not doing the homework, but you get points for doing it, right? But that one, all right, let's make it very clear. The reason to do that at all, these last homeworks that we're doing now, a big reason they're important is so that you hit the ground running in physics 204. That's really what's going on right now. This is so that you start physics 204 not feeling rattled or or rushed or confused or tricked or something like that. So everything we're doing right now is like very much is like the stuff that feeds into physics 204 right at the beginning. Um, so you can bear that in mind, and I'll bear that in mind. And so yes, fine. I just made homework. So homework is 11 is if you've got nothing else to do and you're looking for more points and it doesn't seem that stressful to you or whatever, then try it. But if not, don't worry about it. Homework 11 is what I'm talking about. Um, I hope that helps address the question that was just, or the comment that was just made in the chat. Wait, hold on. But yeah, right. Okay, good, good. No, you're totally not cooked. Seriously. Okay, so I've just done that. That addresses that. Someone else is saying in the chat, yeah, someone else is saying in the chat that they're sort of behind on the last two homeworks because the academic stress is getting to you. Can you upload this weekend? Yes. And especially if by last two you mean like 10, 11. Yes, all of you guys. You can still upload homeworks this weekend. Like I will take homeworks until the very last day of classes, until Wednesday. I will. I would rather not. I think I said this yesterday, but let me reinforce again. Like we're all behind. Obviously, I'm behind. Like the end of the semester is like it's always, it freaks me out a little bit too, or a lot. Um, so it's about playing catch up in a way, all of us here. Like my main point at the end of the semester is to get you the content that I think you need to justify all your work in this course and to help you in the next semester. And my main priority is to like get you grades and get you in a position to optimize your grade so that you can get the best possible grade you can, like given the work that you're doing, all that, the best possible fair grade that you can. Um, so we're all trying to dig ourselves out a little bit at the end of the semester. So yes, there's like leniency and compassion involved, hopefully going in both directions, but certainly going from me to you for real. Um, so I'm just gonna say, yes, you can still be handing things in. I will still take things of any kind, of all kinds, until next week, and I'll understand. Some things I won't give full credit. Like if it's old enough, I might not give you all the points, but I'll give you enough to make it worth it for you. Your main goal is to try to learn this physics, whatever that means, and do well in the course. So you triage and prioritize, and I'm doing the same. Um, but there was something specific about that. But okay, please, what I don't want you to do is like on the last day of classes or something, don't hand me a pile of all the homeworks from the whole semester. Like that's it, bad form. Like it doesn't feel right in either direction to do that. And it's sort of hard to do that without cheating. And we all know that. So like it's just kind of an unseemly thing to do. And it suddenly makes it a hard situation for me. So don't give me like a ton of things on the but yes, yes, you can give me stuff until Wednesday. Yes. Wait. Yeah, yeah, yeah. Like I'll definitely 10 and 11, I definitely get it. Like to be honest to all of you, if you're still handing in 10 and 11, I you probably would get full credit. I'm not even like thinking like I'm going to deduct points for like we're all catching up now. But that's also and also hopefully everything I'm saying in class will help make 10 and 11 easier for you when you go down sit down to do them. Plus, I think they both have a bunch of hints and stuff written throughout. Like those were sort of written with somebody else who went a little deep on them. Okay, so hopefully that, okay, the idea we still all want to do well. You want to do well and you're getting frayed at the edges. I want you to do well and I'm getting frayed at the edges. So the goal is to do this with as much dignity and success as we all can, and then be ready to take a deep breath and then do 204. Okay, just so hopefully that's clear. Now, the only other thing I want to say, as long as these are all fair questions. I mean, I sort of was a little bit more prepared to deal with them a little bit more directly next week, but as long as they're being asked right now, let me check something right now for you also, in terms of the final. This is, we are in spring. We are in spring of 2025, right? All right, hold on, hold on. This is spring of 2025, right? Okay, what I'm doing right now, since someone's also asking, bear with me for a second. I promise I'm looking at something to address these concerns about. Where did it go? Final exam. Okay. I'm okay. One second. The reason I'm pausing right now is all right. I'm not going to get bogged down in this. Here's why I'm pausing right now. You're also somebody in the chat is also asking about like the content of the final exam, which like I'm going to stand by. I was going to get more into on Monday, and I will get into it more Monday, but I do understand why that is a concern. And the reason I'm bumping right now or pausing is okay, I'll just say this. I'm getting bogged down in the document management, but I just learned yesterday, I believe, and you could correct me if I'm wrong, and then we got to get back to content in a second, but I just saw something this morning, through the Google Classroom or anything that I believe Mercedes is in lab tomorrow planning to do some sort of review or prep session for the final exam. Tomorrow's Thursday. I believe you have lab tomorrow with Mercedes. And I just got the impression, and this is not unusual. It's like often what we do. But can you confirm or deny? Did she say that to you? Hold on. You had her yesterday. Okay, okay, okay. Oh, your Tuesday. Okay, okay. So what ha so what did you do in lab yesterday? We, you have it next week. Oh, okay, 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 okay. Oh, you had the board. That's right. You had the board meeting. Oh, right. And the board meeting was like on a rotation thing, right? Correct? It was about circular. Okay, well, which is a little funny. Yeah, okay, okay. Well, I'm glad we're talking about this. All right. All right. Let's just hold the presses for a second. Okay. So maybe there was a slight bump in communication or something somewhere. The board meeting you had on circular motion for yesterday, that's cool because that's material that is good to know. It is good to know about circular motion. It's good to know about circular motion for physics 204, for life, for future. It is part of this curriculum. You got to get it somewhere. So you got it in lab yesterday. That actually saves us some hassle here. Okay, that's like the good news of that. The extra good news of that is that I can answer some questions about it right now if you want, but assuming you don't have a report on it or anything because it was a board meeting, if um if you don't feel like you fully get it or it fully landed with you or whatever, I can tell you that that's not on the final exam. Okay, so whatever that was, it was a one-off. You did your best. You hopefully got something out of it, but you don't have to worry about it any further. I don't think. Wait one second. One second. Okay. And quick question on that. The thing that you didn't get, or I guess we're talking, or I guess we're doing this right now. The board meeting that you had on circular motion yesterday, did it involve like A equals V squared over R at all? Not that, yes. Okay. Okay. So look, you needed to know that. You needed to get exposure to that. It's like important. It will sort of come up a little bit next semester, not a lot, but a little bit. It's a good thing to know in physics. Whatever you got out of it is good. Whatever you didn't get out of yesterday, don't worry about it. It's not on your final exam, and it's not on your final, and you don't have a report or a homework or anything on it. Okay. That's on the one hand. On the other hand, if you're um uh having if you're telling me, and I do, now that we're talking about this, we're saving time from next week to talk about this right now. So if we're talking about this, you're explicitly telling me that you still have one more lab with her on Tuesday. Okay. I just did get a memo from her this morning or late last night that made it clear that she's planning on doing review sessions in the labs. So I gather, I mean, for the final. Okay. So I will confirm with her, but I believe that she'll have a practice session, a review session in the lab on Tuesday about the final. That is perfect, because the reason I was scrambling just now when you asked about this is I want to make sure that the content she had, I want to make sure she has the most updated version of what is going to be on the final before she does that. Now that it is confirmed that she's going to do that, and you're telling me, and it's going to be Tuesday, I will make sure. I mean, I was about to do it right now, but I will make sure that I have all my full decisions about exactly the content of the final exam and exactly how it will go. I will have that a practice exam for her in time for her, in time for you guys to see, and in time for her to walk through with you, or have you do it in that period Tuesday. So in other words, you will have a full look at this final exam, just like last time, before you do it. And you'll have a chance to, see what's going on with her in lab on Tuesday. And that actually calms me down, to tell you the truth, because it is true that in your class, each semester we do a slightly different approach on the final. Like you're welcome to see any past exams you want, but they do change. So it's good that we'll all be on the same page. And that's also why I can't exactly I mean, I have to make certain decisions on, like, well, it doesn't matter. So you'll know by Tuesday exactly what your final exam is going to look like. But I will tell you this much: it will be again like last time. There'll be like four problems or something on, or three. You'll have choices just like last time. Like you'll choose two problems or something, and you're going to take it home and do it home and turn it in just like last time. And so the exact content Tuesday. So does that? So oh, okay. Your lab schedule says, okay, okay, okay. Right. So I understand you're not exactly sure at this moment what the content would be. I mean, of course, the basic answer is it's the material we've done since the last exam. Newton's laws and work and energy is the basic thing. But yeah, you'll know specifically, you'll get a practice document, hope in advance of Tuesday. Like it'll be posted in Google Classroom. I believe, frankly, already in Google Classroom, there is a document that says last year's final exam that is there for you to see and use as a practice document for your final exam. I believe it's there, but I will tell you straight up right now, I think yours is going to be not exactly the same. I think yours is that it says last year's, but it's like 4 semesters ago or whatever. Yours won't be quite that. So you can look at that as a sneak peek and as to get a sense, and you can use it to practice. And there will be similarities. But the most updated version of your exam, you'll know clearly in advance of Tuesday. Whether it's this weekend or what, I'll notify you and I'll notify her. And then Tuesday will be your opportunity to walk through it. Okay. Fine, fair enough. Fair enough. Yeah, there is. Okay, okay. So yes, that is like you're welcome to look at the thing that's already there. I am warning you that I think yours is going to change somewhat. So don't get married to that one, but it's good practice, obviously. I mean, it's a good good first exposure to what kinds of things you need to think about. Okay, okay. And yes, and bottom line, um, okay, and I'll say this too, just to be clear. Generally speaking, what we say is that the final exam is about the material that you did since the midterm. Like, generally speaking, physics is only cumulative. It is all cumulative in that you can't understand the next idea without understanding the last idea. It's like automatically cumulative that way. Generally speaking, our final exams, we just therefore focus explicitly on the material like since the last one. However, it's also true that in the past couple of semesters, sometimes what I've done, this is not a promise. This is what I have to think through. Okay, what I'm about to say. Sometimes recently, what I've done on the final exam is give people make one of the problem choices that you get to redo one of your problems from the midterm so you can do it better and learn and whatever. Sometimes lately I've been doing, and then I've sometimes lately made the other problem like a a sneak peek at the first homework problem of physics 204 so that it really sort of a look back and look forward kind of exam. Sometimes I've done that recently. We didn't used to do it, but we've done it recently. I I don't know which way this is going to go yet. That's what I can't promise you. But those are all possibilities, okay? That's all. Okay, I'm going to move on now. Okay. I mean, hopefully this is somewhat clarifying. Uh, hopefully. All right. So, but these are good questions, and you can ask them again Monday. In fact, I'm writing a note to myself right now to make sure to send the document to Mercedes. Hold on. I mean, I think I already have actually done that note, but okay. All right. So thank you. I mean, I hope. Okay, I don't mean to cut. If there are more questions, you can ask them, but I think hopefully this is I think as clarifying as I can be at the moment. Um, so I'm gonna get back to physics. Um, quick review of what we said yesterday is this. Um, the force exerted, the key point is that the force exerted by a spring has an X in it. It's the first example we ever see in physics of a force that varies as a function of position, right? So it becomes the first example where we actually really have to deal with the fact that work, now I'm talking about the bottom equation on the thing on the sheet, that springs are the first example where we really have to confront the fact that work is defined to be an integral. It's really what makes the integral come alive, right? Because what we need integrals for, we need integrals when the dependent variable, well, we need to integrate work when, sorry, we need to integrate force when force isn't constant. We need integrals when measurements vary in a continuous fashion. And that's exactly what the spring does. The force that it exerts changes at every position that the end of the spring could possibly be. And that means every position. It's not like at 1 meter mark, it's one thing, at the 2 meter mark, it's one thing, at the three, it's like at any millimeter, at any angstrom, at anything you come up with, the very next position, the force is something different. It's a smooth, continuous function of position. Hence, to add up all the force times displacement, force times displacement, force times displacement, force times displacement, we need a technique for adding up a continuous sum of products. That technique is called the integral. Okay, so work is the integral of force with respect to displacement. Spring force is an example where you need to do this integral to really find out what the work is done by this spring force. And so when you do the integral, you get that the work done by a spring to move, like to move a mass from some position, call it x naught, to equilibrium to x equals zero is 1 half k x squared. That's a review of what we're saying yesterday. Now, I mean, of course, you could like memorize the well. What I'm really saying is you can memorize the top equation and you can memorize the bottom. The bottom is a definition and the top is a law. But the middle one, you really need to understand how the middle one followed from the top and the bottom. How can I make a note of that? Okay. Now, like the so we said that one of the first big reasons that we're ever dealing with springs is that they have this property of a variable force. And that was like that's the context of that whole homework 11. It'll be easier when you go back and look at it after these lectures. I think it's all about what do you do when the forces change? And the answer is you integrate. But there's another reason that we look at springs now. There's another reason that we look at springs, and that is okay. Again, right now I'm in principle sort of picking up where I was yesterday. I mean, I'm still sort of saying something that I was sort of saying yesterday, but I was saying it very quickly at the end. I want to say we've been dealing a lot with gravitational forces, gravity. And specifically, I don't just mean we've been dealing with them, but like in this chapter on work, we've been talking about gravity a lot. A lot of the examples in the homeworks are like things going up ramps, down ramps, up hills, roller coasters. So gravity's coming up a lot. We've figured out what the work done by gravity, the work done by gravity is always mgh, just like the work done by a spring is always 1 half kx squared. So we did a lot of gravity, gravity, gravity. Now we're talking about springs. There's a commonality, but I'm sorry, Mr. Garrison. I'm sorry. There is a contrast between the two. There's an important contrast that I just mentioned a minute ago, which is that gravity is a constant force. Gravity, mg, does not change with respect to position. So whenever you're doing the work done by gravity, yes, technically you're doing an integral, but the force always comes out of the integral. It's a constant. So you don't end up really having, you don't have to know a lot about integration to do it. So you get, in the end, the work done by gravity is the force of gravity, mg, times the distance, h. It seems sort of simpler. I mean, I hope because the force of gravity doesn't change from spot to spot. Whereas the force of the spring does change from spot to spot. Okay, so that's a difference between the two. It's one of the reasons we move in our like in our study from gravity to springs. However, there's a similarity between the two that's very important, which is that ultimately both of those forces, gravity and the spring force, we characterize as conservative forces. This is not a political remark. They are conservative forces, unlike the tension force of a string, the normal force of a surface, um, the frictional force of a surface. Those forces are forces. They're real. They're important. We analyze them. They're not conservative. Gravity and the spring, the gravitational force and the elastic force are conservative. Now, and that's like super important, and it's very important for physics 204. What does it mean to say they're conservative? Okay, loosely speaking, just like to have an intuitive picture of what I call a force of conservative, like what am I even saying? Loosely speaking, I'm saying it's a type of force that's probably associated with an equilibrium position, right? Like gravity is always trying to bring you down, like the man. Gravity is always trying to bring you down to the ground. The ground is somehow an equilibrium position. More specifically, if you're on the ground, all the forces are balanced and you won't move. If you're sitting on the ground, you will continue to sit. Unlike anywhere else, if you're sitting above the ground, and you're like, oh, you will move to the ground, right? So gravity has that property, and so do springs. There's an equilibrium position for a spring. Loosely speaking, if a force is a kind of force that's sort of always trying to bring you to an equilibrium orientation, that's a that's a strong sign that it's a conservative force. But um, that's a that's a qualitative way of identifying conservative forces. There's a mathematical way that's important to us to rigorously distinguish a conservative force from a non-conservative force. And it goes something like this. And I know I did say this yesterday, the following, but I'm trying to say it a little bit more slowly and clearly now. So bear with me and please do write it again. I'm going to carefully introduce a mathematical piece of notation right now. Um, okay. Okay. Here's what I mean. The mathematical thing I'm saying is like about integrals from calculus class, right? And there's indefinite integrals, but then there's definite integrals. We tend to be talking about definite integrals here in physics. A definite integral is an integral from one definite value to another definite value, right? A definite integral is the continuous sum of products throughout some specified region on the x-axis. There's a third kind of integral that you may not have seen in a math class. It's called a closed integral, and it's designated with a circle like that. What a closed integral means rigorously, mathematically, a closed integral is a definite integral. It is an integral over a specified region on the x-axis. So much so that like the answer to a definite integral does not have a plus c, if you know what I'm saying. It doesn't have an arbitrary constant in the answer. It's definite. But what it definitely is the integral on along the region from value 1 to value 2 plus the integral from value 2 back to value 1, whatever the value 1 is, right? In other words, a closed integral is by definition, triple equal sign, is by definition a round trip. Now, not like literally round because we're talking about one dimension here, but a, but a definite integral is a bounded integral for which the starting boundary is the same as the ending boundary. That is what a closed integral is. It's the integral around a round trip, a there and back. Okay, that's like a math thing. It's a type of integral. And stop me if that doesn't make sense. But again, that's like a math. I want to be clear. That is a math thing I want you to know. I need you to know for Physics 204. It's not going to get any harder than that. It's just like a concept. Okay. But but I'm not saying it like I think you already know it. I'm not assuming you've already ever seen that before. I understand you might not have, but I'm just telling you that it's true. Okay? Um Now the physics application of that is that is that is that any force for which the closed path integral is zero, like necessarily, that force we call conservative. I'm going to give you an example in a second, obviously, or I'm going to like show you what I mean. But I'm in effect using the idea of a closed integral to define a physics concept called a conservative force, or to define a type of force in physics called conservative. Um, yeah, I'm saying uh, we integrate forces from here to there, and we call that computing work, right? I'm saying we can always, if we want, integrate the force from here to there and back. And we would call that like the work done throughout a round trip. I'm saying if the work done by a certain force over a round trip is definitely always zero, then we call that force conservative. That's what I'm saying. And I'm saying this applies. It turns out this statement applies to the gravitational force and to the spring force, but not to the tension force or the friction force or the normal force. Okay, that's what I'm asserting. Let me give you a quick, um, let me show you why I'm saying that because to be totally blunt, often once I think you're following me. I hope you're following me. Often when I try to say this math thing and then this physics thing, often what it seems like to many people who are following and who are paying attention, and I think maybe what it felt like to me when I first saw this, I don't remember. Um, I think many people consciously or unconsciously think, all right, I get round trip. Okay, round trip, I get you force out, force in. Okay. But it sort of seems like whatever that you could sort of see why you might sometimes get zero or not. But it sort of feels like, wouldn't you either always get zero if you're doing a round trip or never get zero? But why would you sometimes get zero with some kind of force and not with another? Like it's sort of whatever. So I'm going to show you. I'm going to explain somewhat quickly right now. It all has to do with negative signs. 100% it has to do with negative signs. What I mean is this. If you um think about friction or something, a block is going along a table and friction is acting on the block, right? So you're pushing the block along the table, like to the north, and while that's happening, the friction is like pushing to the south, okay? If we want, and say you push the block for 10 meters, okay, so think about the work that the friction is doing on the block. If we push the block out to the north, like for 10 meters, while we're pushing out to the, while the block is being displaced to the north, friction is pushing to the south, right? Friction's opposing the motion. So while the block is going out, friction's doing negative work on it. And of course, it's like slowing it down, or certainly trying to slow it down, right? So while the block is going out, the friction is exerting and is doing the friction force is opposite to the displacement. So the work is negative. Then say we start bringing the block back to make and complete a round trip. So we start bringing the block back. Well, now the block is moving to the south, right? The direction of the displacement has changed. But of course, so has the friction, because like that's how friction works. So now the block is displacing to the south, but now the friction is to the north. So again, on the way back, the force of friction is doing negative work again. And of course, it's friction. Like it's again trying to slow the block down, right? It's not like trying to help it now suddenly. So on the way out, friction does a bunch of negative work. Call it -5 joules. I don't some it's negative blah joules. And on the way back, friction again does negative blah joules. So the total amount of work that friction will do along a round trip would be -2 blah joules. A lot of negative work. It just accumulates. So it will take away a lot of kinetic energy from the block. In other words, what I'm really saying with friction is I don't care whether you push a block out all the way 10 meters or you push it 5 and then you push it 5 back this way. No matter what, friction is sucking energy out of the block and never giving it back. Friction is non-conservative. Tension, if you were pulling the block with a rope, the same thing would be happening, only you'd be helping the block with that rope. So you'd be just be giving energy to the block no matter what. The block doesn't care which direction you're going in. And hint, or like spoiler alert, when I say like the tension doesn't care which direction you're going in, or friction doesn't care, it's just like going to be sucking energy because there's no equilibrium position associated with friction or tension. They're not like trying to get you anywhere. They're just like reacting to your motion. Okay, so friction and tension, if you do a round trip, they just accumulate a whole bunch of energy gain or energy loss as appropriate. Contrast that with gravity. If you throw something up to a height h, you take a mass and you throw it up to height h. So it's going up, it's going up, it's going up. Gravity is pulling it down, pulling it down, pulling it while it goes up, right? The displacement is up, the force is down. So the work is negative. This, like we said last Wednesday, the work is negative. It's like negative mg times positive h. They're in opposition. The work is negative. That's why the block slows down. So it's like losing kinetic energy as it gets to the top. Fine. But then it gets to the top and now it starts falling down. Now, the displacement direction changes when something's coming back down to complete its round trip under gravity. The displacement changes its direction, but the gravity force did not. The gravity is still pulling down, right? And again, this is kind of like lab 5. Like friction flips, but gravity doesn't. Gravity's always trying to just pull you down. It doesn't care which direction you're going in. It's trying to pull you down to an equilibrium that we call ground. So when the object's on its way down, now displacement is negative, force is negative, like negative mgh, negative h, negative times negative is a positive. They're in agreement. So now it's positive work on the way down. Now gravity is adding kinetic energy on the way down. So on the way up, gravity did negative mgh. On the way down, positive mgh. The net work. So on the way up, gravity slows you down. On the way down, gravity speeds you up. On the way up, it took away kinetic energy from you. On the way down, it gives you kinetic energy. And it's all because of that negative sign, like that it stayed there the whole way with gravity, but it flipped with regard to friction, right? So the net work done by gravity over a round trip is zero. It's like negative H plus positive mgh. And same argument you can make in your head. You can picture the same thing happens with the spring because the spring's always trying to pull you to equilibrium. It does the same flippy thing that I just described. So the work done by forces like spring or like gravity, the work done around the round trip is necessarily zero. So we call those forces conservative, unlike tension or normal or friction. All right, I'm going to pause for a second. Um, I'm going to pause for a second and then I'm going to use this concept. But can I just get like show of hands? Is it clear enough for me to move on? Can I mean, or any questions? Does that make sense so far? Thank you. All right. Awesome. Thank you. Awesome. Awesome. Okay. Great. So I'm going to move on. So that's conservative forces. Now, what do we do with that? Then be, oh, thank you. Wow. Okay. Thank you. I appreciate it, direct chat person. Um, okay. Okay. I know I've now written this equation down here like a couple of times now. Let me now finally explain what I mean by it. Um, I'm saying now I want to talk about this idea that, of course, you've heard before of potential energy. I mean, many of us have heard of potential energy before. Here's now where I want to, I mean, it's a very useful concept, but where it comes from is this, first of all, is this idea of conservative forces. Potential energy is not a thing. I mean, it's not relevant or meaningful or accurate. It's not relevant or meaningful at all when you're talking about non-conservative forces. There's no such thing as the potential energy due to friction or something like that. Where potential energy comes up is when you have conservative forces. The idea of potential energy is this. If you have a conservative force, that means you already know in advance that if you let a conservative force do work over a round trip, you know whatever kinetic whatever kinetic energy is lost like on the way out for that round trip is necessarily going to be gained back on the way in if it's a conservative force. Let me back up for a second and say this is all assuming something that I did explain last week, but also maybe again too quickly or something. One thing I'm assuming in the background here is that work is the transfer of energy, right? I mean, I definitely did say this, but let me drum it in again. Work triple equal sign, what work is the path integral of force. What work is the accumulated effect of force throughout some displacement over some path. That's what work is. What work does, double equal sign, is it transfers energy. When I do positive work on you, I give you 1/2 mv squared. And where did it come from? It came from me. I lose 1/2 mv squared. Like I'm just reminding you, but I should write it down now, but I don't want a rabbit hole. My God, I'm like Zoom. I really okay. Anyway, Zoom gets so freaked out by me. I can't imagine why. It's constantly saying like, "Dude, it doesn't look like you're speaking English anymore, dude. It doesn't look like you're talking." Um, it doesn't say dude. Uh, 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 Work. I mean, the equation I'm in my mind is like work W equals 1/2 mv squared minus 1/2 mv squared naught. Like that is a thing that you want to have in your mind. When I do positive work on you, I raise your 1/2 mv squared by exactly that amount of joules. And where did you get that 1/2 mv squared from? From me. I lost that amount of 1/2 mv squared. If I do 5 joules of work on you, you have 5 joules more of 1/2 mv squared, and I have 5 joules less of 1/2 mv squared. 1/2 mv squared is kinetic energy, right? And again, I'm just quickly summarizing again. So the whole idea is that when you do work, the consequence of that is transferring energy. What is energy? It's the ability to do work, to do just that. Is that a circle? Sort of, but only to the extent that like money is a circle, right? I mean, just reminding you, energy is the ability to do work. Work is the transfer of energy. When we do work, we pass energy from one system to another. What is the significance of having a lot of energy? That you can do that. You can interact with another system and change something about it at your expense. Why would you ever want to do that? Because energy ultimately comes in different forms. So you can make trades. You can trade your kinetic energy for thermal energy. Like you can slow down so that you can heat up, et cetera, et cetera. Okay, so but that's the whole idea is that work is the transaction and energy is the commodity. Okay, that's in the background, the assumption that I'm like making as I talk about this. Now, but the other until this moment, the only well, I just said it. I just said like the transaction, I mean, work is this transaction where you're passing around the commodity known as energy. Now, what I just said was that the reason you would ever want to do that is so that you could trade energy from one form to another. I mean, and quite frankly, that's not the only reason, but that's like a pretty vivid reason. But up until now, we only had one form of energy called kinetic, 1/2 mv squared. So, like, what? I mean, so it was kind of just like this big circle. What I'm saying now is, well, if all the forces doing conservative, if all the forces doing work are conservative, then we kind of always know something in advance. We know if I throw a block up into the air, it's going up, it's going up. Gravity is doing negative work on it, negative mgh, negative mgh. It gets up here. Now it's at the top. It pauses for a minute. No, not for a minute. I mean, it pauses for a moment. Or maybe someone's even holding it now at the top at some height h. So it's sitting still. So it has no kinetic energy anymore. It lost all of its kinetic energy on its way up. It's sitting still, right? So it seems like it has no energy, no ability to do work, no ability to interact with another system and change any aspect of that other system. But however, the negative work that was just done on it to suck out its kinetic energy, that negative work was done by a conservative force called gravity. We know, we know that if we let this thing fall down, we know exactly how much kinetic energy it's going to gain on its way back down. It's going to gain exactly as much kinetic energy as it lost on the way up because we know that net for the whole round trip has to be zero because this force is conservative. So we can save ourselves a lot of hassle and computations by just predicting, by knowing in advance. You know what? When this thing is up here, if we let it go, it is definitely going to gain an mgh amount of 1/2 mv squared. on the way back down. We know how much, in other words, by holding it here, it really does have the ability to interact with something else and change. Like we could drop this thing now and it could land on something and move it. This thing that we're holding up here could be water, and the water could fall down a waterfall and hit a turbine, like a mill, like a spinny thing, and then start moving logs down a river. Not to be weird, but right, like there is an ability, a capacity to do work that comes in from just being in an unstable position under the presence of a conservative force. That's what, like, or to be better, if you've moved something away from equilibrium under the presence of a conservative force, the mere fact that the object is not at equilibrium anymore, like really, and it's not stable anymore, really means we know what's going to happen if it moves toward equilibrium, and we know that it can do work. So why do we have to wait for that to happen to do the computation? What we say is, you know what? So look at this integral here at the bottom of the page. We're saying the work that the conservative force would do to take the object back from an arbitrary location, x naught, to zero equilibrium, the work that that conservative force would do, which is precisely the amount of work we did on it to get it there in the first place, that is kinetic energy, like waiting to happen, totally predictably, totally reliably. So we say, oh, this object is storing energy in the form of potential. We say that an object at a height above the ground or a mass at a displacement from a spring equilibrium, even though the thing is not moving, even though the thing has no kinetic energy, we say it's storing energy because we know what's going to happen to it. We know the only way it got there was we did a certain amount of work on it to get it away from equilibrium. And we know it's going to, so we took energy away from it. We know it's going to get exactly that amount of energy back if we let it go to equilibrium. So we say it's storing that energy, that exact amount of energy. What amount of energy? The amount of work that the conservative force will do to bring it back to equilibrium. We say it's storing it as potential. So potential energy is defined to be the work that a conservative force would do to bring back an object to equilibrium. Or if you don't, that's one way to look at it. To me, that's the easiest way to look at it. Another way you could look at it is this, if it's easier. Like, that's just to say it's the amount of work we had to do against the object to bring it away from equilibrium. Whatever we did to the object to bring it away from equilibrium, whatever energy we sucked out of it is the same as the energy that it's going to get on its way back. So instead of like waiting all day to do two computations, we just say when it's sitting there, if an object is sitting there not at equilibrium, then it's storing this energy we call potential. Okay, so in short, I'm saying um so if kinetic energy is the ability to do work due to motion, and that's what it was. Kinetic energy is like 1 f mv squared. The more you're Ving, the higher your V is, the more you have the ability to crash into something else to push or pull something else and give it some of your V, right? That's what kinetic energy is. Potential energy now is also the ability, it's another form of energy. It's the ability to do work, but it's the ability to do work uh, not due to your motion, but due to your orientation, your position, how you're arranged relative to another object. Specifically, the more unstably you're arranged, the farther away you are from equilibrium, uh, the more potential energy you have. Now, and mathematically, we just, and, okay, so it's mathematically, it's the work that had to be done on a system to displace it from equilibrium. The farther it is from equilibrium, the more work we have to do to get it from equilibrium, the more we took energy out of it to do that. And the more energy we'll get back if it ever goes back to equilibrium. So while it's sitting there in between, we say it's storing it as potential. Okay, what's the advantage of this? We're almost done for today. We have 9 minutes. The advantage of this is then thus. Okay. We're almost done. We this might be the last page. I'm saying the significance, the utility of potential energy is once we define, now again, please remember this whole concept of potential energy only applies when we're talking about conservative forces. But if you have a system where all the forces acting on it are conservative, then 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 when you try to move the system away from equilibrium, you do work on it, you give it potential energy. You do negative work on it, you slow it down, but you're giving it potential energy. Then when the system is let go and it starts moving back to equilibrium, it's losing potential energy, but speeding up, gaining kinetic energy. The whole logic, but they're the same. The logic of this is that at any given spot, any given location, x1, x2, x3, any given x for a system, it has a total amount of energy, which all of its kinetic at that spot, plus all of its potential at that spot. And that entire amount has to be a constant. has to be a constant from the way that we just defined potential energy. I mean, potential energy that you have is, we've defined it to be a prediction of the kinetic energy that you're going to gain as you go back to equilibrium. And the kinetic energy that you gain as you go back to equilibrium is necessarily exactly whatever kinetic energy you lost on your way out from equilibrium. Again, all assuming that the net work done on the system for a round trip is zero, right? This is all assuming conservative forces. But if the force is conservative, what that means is that at any given moment, it has a sum of kinetic and potential energy. It has a total amount of joules. And that sum we call its total mechanical energy, all of its kinetic plus all of its potential, we call total mechanical energy. Whatever that value is, has to be constant throughout all the motion. So this is, of course, you've heard of conservation of energy. And I mean, you've heard of maybe all of these concepts before. I'm maybe now putting them or trying to put them in a slightly more sophisticated mathematical way involving integrals and everything. But the bottom line is, for a system on which no non-conservative forces are doing work, the total mechanical energy of that system is a constant. Total mechanical energy means the sum is defined to be the sum of all kinetic plus all potential. Call that capital E. Capital E must be a constant, E naught, for every value of X through the system. In fact, okay, I'm going to write one more note, and then we're okay. We have 3 minutes. Okay. I'm saying, just note, so to conserve energy, conserve mechanical energy means to keep your total amount of energy, all your kinetic plus potential, as one sum that doesn't change. Doesn't change with respect to what? Doesn't change with respect to place. Whether you're at X1 or X2 or X3, H1, H2, H3, no matter what place you are, if you when your as your kinetic energy goes up, your potential energy goes down, and vice versa. They always have to equal a constant, which ultimately means, I mean, as opposed to like making it keeping a constant from time to time, that would be something else. Energy is conserved from place to place. And what that means, the utility of that, is it means once you have a conservative system, like we're talking about, it means there's always a one-to-one correspondence between speed and spot. Like your 1F mv squared, like say we're talking about springs, your 1F mv squared plus your 1F kx squared over here must equal your 1F mv squared plus your 1F kx squared over there. Or if we're talking about gravity, your 1F mv squared plus your mgh over here must be your 1F mv squared plus your mgh over there. So as long as you, so there's always a one-to-one correspondence between h and v, or x and v. There's a, if you know the speed, if you name the speed, I can name the spot. Or if I name the spot, you can name the speed. That's the point of this. There's 1 minute left. I'm actually done. I just want to say one thing you might have also noticed in the class. Punks think it's always awkward. The class evaluations, please do them. We'll talk about this another time if you want. They really matter more than you think. They actually matter. We don't know who writes them. I swear I don't know. I don't want to know. I don't know who you are when you write them or anything like that, but they actually do matter. I promise. Um, And in this court, if you do the evaluations and you just screenshot the fact that you did it, like whenever you sign in and you do, and then it gives you like a whatever a confirmation, don't just screenshot that. Don't screenshot what you did or your or anything like that. But if you just screenshot that you did one and you submit it in the portal, you'll get points. You get 10 points for each one that you do. Technically, you're supposed to do two for this class, one for lecture, one for recitation. Of course, they're the same instructor and the same everything. You can do the same. It doesn't matter, but we need the data. So if you do both, please, at your leisure, I'll try to stop and make time for it next class if I can. But if you do it and you just submit the evidence that you did it, don't submit the thing itself. You'll get 20 points for that. Okay, so oh, you're very good. No, okay, thank you. It means thank you. Okay, so I'll see you. I'll be in communication. I'll see you. Yes. Okay. Have a good, thank you. Bye. Have a good one. Yes, definitely. Okay.